Well, thanks for having me. I'm going to build on some of the discussions that we've had today, but because of time, I'll just launch right in. And let me use a pen. So let me start with the fact that in the real world today, we are having massive agricultural expansion. So we finally had a good satellite study a couple of years ago, and it found that we were expanding annual cropland, not agricultural land, by 10 million hectares a year. There's evidence that permanent crops like oil palm, rubber are adding another 1 million hectares. So we're essentially clearing an area almost the size of England per year just to produce increased food. Some of this is due to biofuels too. A lot of it is due to biofuels too. And this basically, all the areas in red are the cropland expansion. Now, this number, by the way, is a net number. So there's also about 10 million hectares of land. So we're really clearing about 20 million hectares of land, and almost 10 are actually leaving cropland use, and many are reforesting, and I'll come back to that because that's important. So we have even more damage being done because the gross changing is more like 20 million hectares. So basically, we're on a pace where just for cropland alone, we're going to clear an area the size of Chile in the next, I'm sorry, India in the next 30 years. And that's not even counting pasture, which is the primary driver of deforestation, for example, in Latin America. And when you really talk to people, how do we actually feed the world without destroying the world? It's enormously challenging, even if we don't add biofuels. So that's the real world that we're in. And biofuels are an almost staggeringly inefficient use of land. Let me see if can I move that? So basically, if you have 1,000 joules of solar energy and you turn them into corn ethanol, maize ethanol, you get only about 1 joule net energy in the ethanol. Sugarcane ethanol 2, this is 3.5, not 35 for switchgrass in the most optimistic location estimated by DOE. So this is 3.5. And if you use PV on a net basis, this is even in the past, you're getting about 150 joules. So what this means is that, and we did an estimate, even viewed optimistically for future cellulosic ethanol, and all these areas in yellow or orange, you'll get a minimum of 100 times more usable energy using PV than using biofuels. And then on top of that, electricity has about a 3-to-1 benefit when you're using it in a car or even for a heat pump. And so you're really getting about 300 times more usable energy. And what this means is that even if we had, for other reasons, even if we had spare agricultural land, if you had 100 hectares of spare agricultural land or 300 hectares of spare agricultural land, you could use 1 for PV and reforest 299. Or you could use and get the same amount of energy as if you used all 300 for bioenergy, but you'd get 300 times the greenhouse gas reduction. Now, we have had these extraordinary estimates of bioenergy potential, and frequently in the IPCC, you'll see estimates saying, 230 exajoules of primary energy. Now, how much is that? Well, in 2000, all of the world's harvested biomass for crops, crop residues harvested, grasses eaten by livestock, and wood were about 230 exajoules. So in effect, people have been claiming that we could double the harvest of plant material, and somehow or other this would be good to the climate, even though this existing harvest of plant material is responsible for about a quarter of all the carbon in the atmosphere. And the continued production leads to even more. So when you see that, it doesn't mean that this has been exaggerated. It means somebody made a mistake. Somebody made a basic accounting error. How could someone argue that the best uses of this land are to grow biomass with 1 or 2, not 1 or 2%, 0.1 to 0.2% conversion efficiency, instead of using land for other purposes, particularly when we're desperate to avoid conversion of land just to feed ourselves? And the answer is that there were accounting errors that basically double counted biomass. Now, if you go back to the 2001 IPCC report, this was their claim. They said, look, there's 3.1 billion hectares of potential arable land. We're only going to need 1.7 billion. That leaves us with 1.4 billion hectares. What if we use all of that to have high biomass yields? And the problem is that 1.4 billion hectares of land is basically the world's forests and most wettest woody savannas. And they just treated that land as free. Of course, it stores carbon. Then we see studies saying, well, look, what if we have regrowing forests? A lot of those regrowing forests, the growth is due to CO2 fertilization itself. About 10 billion tons of CO2 is being absorbed by the world's forests because of the higher carbon dioxide. We already build that into climate estimates. What if we instead use that increased forest growth for bioenergy? Yes, but by definition, that increased forest growth is sequestering carbon. So it's just double counting. What about all abandoned land? We get lots of estimates. We can just use abandoned cropland. And remember what I showed you is that for every 2 hectares of agricultural of cropland expansion, 1 hectare is abandoned and already reforests and is already therefore sequestering carbon. So this abandoned cropland is not free. Additionally, grazing land in some estimates was viewed as free. There was often just calling wetter savannas other land. What if we just take wood from other uses, but it's already being used? In short, this gigantic estimate of bioenergy potential, basically almost all the estimates of bioenergy potential, are based on counting land, biomass, or carbon that is already being used. Now, I hate to say it, but this China study we just saw is a typical example of a new kind of error. And this one is that, well, I can use land and have no cost to using that land if others reduce their land use requirements, right? So if others have diet changes, if others reduce their food waste, if others have yield gains. But the point is that those other changes will already have benefits for the climate. They will help us avoid land use change, or if not, land will reforest. So it's like claiming credit for the work of others. So if I take $100 out of a bank account, it costs that bank account $100. If others instead add $100 to the bank account, that doesn't mean that I'm not making the bank account poorer, that I'm not taking out $100. It just means others have done other things. If I don't take out $100, the bank account grows more. So none of these changes are relevant to the question of biofuels. What you have to say is we have to compare the use of biofuels in a world, if you have these changes, with or without biofuels. And if we don't have biofuels, then we will save land and we will have more land stored. So again, it is treating land as free. Okay, let me show this in a more specific way. So here's a typical life cycle calculation for biofuels. And here we have petrol or gasoline. And here's the mining emissions. Here's the refining emissions. And of course, for gasoline, they're not very high. And however, this is what comes out the tailpipe of a car. So the exhaust pipe, 73 grams per megajoule. And this was a JRC study. Well, growing the grain had more emissions, fertilizer, than just mining oil. That makes sense. Refining has more emissions. And if you actually, what you see is not only do you have this exhaust pipe emissions, but about 50% of all of the carbon in a grain is released during fermentation. And if you add all of that up, you'll get a large greenhouse gas increase. So where does the greenhouse gas reduction come from in these life cycle calculations? The answer is that they essentially assume a credit for plant growth, that the growth of the grain absorbed all this carbon, and this grain cancels out the biogenic emissions, and with that, you can get a greenhouse gas reduction. Now, the size of this reduction therefore depends on these numbers. But here's the critical point. It takes land to grow plants. Where's the cost for the land? Where's the cost for the land? The answer is this analysis treats land as free. We have this enormous struggle to try to store carbon, sequester carbon, natural climate solutions, avoid clearing land. We have a fixed amount of land in the world, and the typical biofuel analysis treats land as free. So here's one way to think about it. The benefit of biofuel is using land to produce plants, to displace fossil emissions, but the cost is not using land for some other purpose. And that obviously has a cost. Now, how do we measure the cost of something? Well, it's the cost of not using it in another way. The cost of any asset is what other people or you could use it for otherwise. That's the cost of using it. It's called the opportunity cost. It's maybe one of the single most basic concepts in economics. And what these typical life cycle calculations do is treat the opportunity cost of land as zero. Okay, now I actually kind of coined, I guess, economic modeling for indirect land use change, but I've come to conclude that that's the wrong way to do it. And here's why. It confuses two different analyses. One question is, what is the effect of a human activity versus no human activity? When we want to know the emissions of something, that's what we evaluate. And what an economic model tries to do is, what is the effect of one human activity versus an alternative human activity? In other words, it tries to predict if we don't do one, given a certain policy, what's the other one we're going to do? And that's a different question. And let me illustrate this. So what's the carbon cost of driving a large car? Well, we know how to do that. You look at the carbon coming out the tailpipe of the car, the exhaust pipe, use a biophysical model, say on average, and we come up with a number. So might be a typical number, 84 grams of CO2 per kilometer. Well, what if you did an economic model and said, well, what happens if we don't drive large cars? Well, it would probably conclude that we drive small cars. And let's say a small car, the emissions are half. So, but does that mean that driving a large car only emits 42 grams, only emits half of the carbon? No. Driving a large car emits 84 grams of carbon per CO2 per kilometer. And this just means that this is the alternative that's being compared. And that doesn't tell us what the real emissions are. And in fact, if you did an economic model that way, you might conclude that driving a small car has negative emissions. Why? Because the alternative would be driving a large car. But obviously, driving a small car doesn't have negative emissions. So what's the cost of using land? The answer is not using it. And that means allowing it to hold carbon in native vegetation. Well, you can do that in two ways. So one is, if we take a typical hectare of maize land in the US and we allow it to reforest, even assuming only 3 tons of carbon per hectare per year, when you translate that into the opportunity cost for biofuels, with a very generous credit for byproducts, the cost is 150 grams of CO2 per megajoule. Well, if driving a car, this is not even counting the production emissions. This is just the land use cost. Driving a car is 74, so it's almost double. Well, what is the latest GREET model, which incorporates the GTAP model from Purdue? It claims that the land use cost is only 7.5 grams per megajoule. What's that basically saying? It's basically saying that the use of more or less the most productive farmland on the planet is almost free. The cost of using it is 5% of the value of just letting that land reforest. It's like saying the value of that land, the alternative use of that land, is having some sparse weeds. Now, what's even another way to evaluate this cost? Well, how do we evaluate the cost of any fixed input to something? Well, if you're going to make a car, you have to start by making a car factory. And we know if this is significant, you should take some of the emissions of building a car factory and assign that to each car. Well, the cost of making crops includes the cost of making cropland. And that means taking this vegetation and turning it into this vegetation. And that has carbon losses. And what we should do is assign a portion of those losses to each ton of crop, and therefore to each ton of crop that is used for a biofuel. Now, if we do that and just say what on average, just on average, is the cost, the land use cost of producing a biofuel over 35 years, so 35 years of biofuels, the land use cost of producing the crops that goes into the biofuels, again, with a very generous carbon credit for byproducts. These are the land use costs. This was a paper in Nature in 2018. And for each of these crops, the gray is the cost per kilometer. And what you see is they are dramatically higher, just the land use cost, than the emissions of gasoline and diesel. And if you use solar, it's like this. So if we just say the cost of producing, the land use cost of producing, let's say the wheat that goes into wheat ethanol is the average amount of carbon we lose over 35 years to produce the wheat that goes in ethanol, that's the cost. Now, if you turn that into an ILUC number, say that's the cost equivalent to an ILUC, for those people familiar with those numbers, that's the number. And look at these numbers. They're staggeringly high. So for a biofuel to be good, since this is the number, since basically, let's say this is only the land use cost, so not even for the production emissions, the land use cost has to be a tiny fraction of the average cost in terms of land conversion that we have to produce the crops that go into biofuels. Okay, now here's another way to say one of the problems with using these economic models. So the economic models say, hey, look, the price goes up, what happens? And one of the things they can say is, well, because the price goes up, poor people around the world will consume less food. And that gives a greenhouse gas benefit. So here's what's actually physically happening. When we grow crops, why isn't growing maize a greenhouse gas reduction strategy? What happens to it? So we're emitting all this carbon. What happens to the carbon in the maize? The answer is that people and livestock consume that carbon and emit it. And if the price goes up and people consume less, well, we still have the same amount of carbon emitted from the tailpipe of the car. We still have the same amount of carbon absorbed in land, but people and livestock consume less carbon. So instead, we're getting a greenhouse gas strategy by increasing global food prices, according to some of these models. And therefore, poor people around the world eat less, and therefore they emit less carbon dioxide. Now, this seems like a joke, except I had a paper in Science with JRC colleagues in 2015, and we showed that the US models, US government models that find greenhouse gas benefits, even within the ILUC calculation, all of the greenhouse gas benefits that they estimated came from the fact that they estimate that poor people around the world consume less food, emit less carbon, and that translates into the greenhouse gas benefit of the biofuels. I don't think that's true over more than that, very much the short term. You get this price increase that people supply, but if that were true, that's a worse result. Okay, now the other question is, can we even do credible economic models? I'm sorry, this is, so this is what you need to do that, right? Okay, let's say we just have 10 crops and livestock products. Well, we need demand elasticities for all 10. We need supply elasticities, but we need two kinds. One is the expansion elasticity. One is the intensification elasticity. If you have 10 regions, that means you need 100 demand and 200 supply elasticities. Now, one of the benefits of the models is supposed to be that you look at how changes in the consumption of one leads to changes in consumption of another. And you need 9,000 cross-price demand and supply elasticities each. And that's before you even factor in trade. So you need literally hundreds to thousands of elasticities to do a model of this type. Now,
2 minutes, Tim.
Okay. The economists know that basically to do that, you need an instrumental variable. I will go quickly since of the time. How many have been properly estimated? Almost none. Simple way to check the model results. Here is models that claim that the greenhouse gas emissions of different vegetable oils. Notice how much higher it is for palm oil. Do they have cross-price elasticities to suggest that? The answer is no. They just have simple estimates. And basically, if you look at the price of soybeans and palm oil, they move almost identically, which means that they're substitutes, which means that if you increase demand for one, you're basically increasing demand for all, which means these numbers should basically be virtually identical. Okay. So let me just finish by giving one more argument for the carbon opportunity cost of land. Why do we even have carbon accounting? Why do we have life cycle accounting? Well, it's largely because we don't have a perfect global carbon price. And what would happen if we had a perfect global carbon price? Well, we can't have it for lots of practical reasons, but it tells us what the most desirable accounting would look like. If you, let's say it's $100 per ton, let's just assume that's the perfect price. You burn oil, you pay $100 per ton. You clear forests, you pay $100 per ton. You allow forests to regrow, you are paid $100 per ton. Now, what would that mean? It means that using land to store carbon is extremely valuable, which means using land not to store carbon becomes extremely expensive. You have to forego, you either have to pay this huge amount to clear land, or you forego being paid this huge amount to reforest land. And all of the production decisions, including for biofuels, reflect this cost. Now, what's another way of saying it? We don't need any other accounting. This is what happened. What does that mean? It means we would be valuing land for its carbon opportunity cost. Now, we can't have a perfect global carbon price for political reasons, for practical reasons. But what this tells us is if we were valuing land properly for climate purposes, we would be valuing it for its carbon opportunity cost. And if that were the case, basically the same numbers I showed fly, biofuels would be never even thought of that involve the dedicated uses of land. So here's my summary. Extremely inefficient. The biofuel analyses in various ways have viewed land as free, double counted biofuels. The economic models are not actually what we should be using. We should be using opportunity cost. We should be looking at what is the average, at least the average cost of carbon lost to produce crops. And we should be really using the carbon opportunity cost. So thank you very much. Sorry for taking too long.